Hello, I'm Russell Klein. I'm a program director with Siemens EDA. I work on the product Catapult, which is a high-level synthesis tool. I'm going to be talking to you today about system verification with MatchLib. So I'd like to start with a little bit of the motivation behind today's talk. How does it tie into real-world challenges that designers are seeing? Then I'm going to do a brief introduction of MatchLib. We have some longer presentations that do that, but we need at least a beginning basis of understanding what it is so that the rest of the talk will make sense. We'll then talk about how to model an AXI bus in MatchLib, and then talk about how we can bring a processor model into a MatchLib simulation. We'll be talking about 3 different processor models: a host code execution model, a fast instruction set simulator, and an RTL model. And then we'll be tying this into a simple design and showing what the results will be on a realistic workload. So we all know that system-level verification needs to be done early. RTL is really available too late in the design cycle and runs too slowly to be a viable approach for exploring different alternatives within the system and verifying and debugging problems that you might find. Now, emulation and FPGA prototypes have enough performance, but they're generally available even later than RTL is. Now, virtual prototypes can be available early, but the challenge here is that, especially at the level of the communication structures within the design, they might not match the final design. There's no linkage between the input to a virtual prototype and the language that describes it and the final RTL. It kind of violates the precept that you should verify what you build. In a virtual prototype, which can be very valuable in certain contexts, you may not be verifying the thing that you're building, and that can cause challenges. So MatchLib is a synthesizable communication framework, and we can synthesize it through a high-level synthesis tool like Catapult. It enables you to very early on do some system-level verification and be able to look at performance in a way that's really not possible without it. It's higher level than RTL, which is going to give you much better performance, and it is throughput accurate with the final implementation. And with high-level synthesis, we have an automated path from the high-level environment to the RTL, and a way of verifying the consistency between those 2 models. So we can prove that the synthesis, the high-level model and the synthesized model, are in fact providing the same functionality. Now, with this path from an abstract model to a detailed model, with functional blocks, we can take high-level synthesis and use those to be able to model and simulate at a high level, but implement at the RTL level. And with MatchLib, we now have the ability to bring in communication elements that can be modeled and simulated abstractly, but then synthesized down to RTL. And we've got a number of presentations that talk about this entire design flow. My colleague Stuart Swan goes out and talks about this on a regular basis. What I'm going to be talking about today is, if we have some functional blocks and some communication elements that are all modeled at an abstract level, how do we bring in other IP that's not modeled through high-level synthesis that needs to be part of the system-level simulation? And that's going to be the focus of today's talk. So we're going to start by describing MatchLib. What is MatchLib? Well, first, it's a clever acronym, a modular approach to circuits and hardware library. But it's also a little bit of a pun, because MatchLib describes the fact that the abstract representation of the communication structure matches the throughput of the RTL that's generated when it's run through high-level synthesis. Now, MatchLib was originally developed by Nvidia labs while creating a machine learning accelerator. The challenge they had in front of them was they needed to try out a number of different communication topologies between the computational elements in their accelerator. And using the traditional virtual prototyping approaches didn't get them close enough in terms of model performance. They couldn't afford to design everything in RTL, and they really couldn't afford to be significantly wrong on their performance estimates. And so they invented MatchLib in order to meet this requirement. So MatchLib is a library of reusable communication models and functions. They've got a set of verified functionality, and the quality of results that we get through high-level synthesis is going to be ensured if we're using the library as it's delivered. It makes very heavy use of templates and parameterization, which enables this library to be able to meet whatever communication topology you're going to need within your design. So the common hardware communication components are modeled as C++ functions, C++ classes, and SystemC modules. MatchLib also contains a number of test bench components. Now, MatchLib addresses complexity and risk. If we look at today's designs, they're often processing huge amounts of data with large sets of intermediate results. If we look at machine learning, computer vision, 5G wireless, in all of these domains, there are very large data sets that are flowing through the design. And what we find is that the architecture of the memory and the interconnect and the management of the movement of the data often has a bigger impact on the power and performance of that design than the computational elements themselves. And what we find is that it's evaluating those memory interconnect architectures at the RTL level just isn't feasible. It's too late in the design cycle, and they run too slowly on the amounts of data that need to be run through the design to be able to meaningfully do a number of different candidate evaluations. What we're also finding is that the most difficult and most costly problems that are found during system integration between hardware blocks and between hardware and software. And if that integration first happens at the RTL level, it's very late. Fixing those problems is going to be very costly, and it doesn't afford you an opportunity to do any course correction when you do find problems. MatchLib lets that integration occur much earlier and makes fixing those problems a lot cheaper. And so let's talk about how that works. Now, the folks at Nvidia, as I mentioned, they were building a machine learning accelerator. So they had an array of processing elements, and they needed to look at a number of different architectures for passing the data, getting the data to those computational elements, and then storing the results and moving on to the next level. So at a functional verification level, MatchLib allows you to describe your communication mechanisms and run them at a very abstract level quickly. But then we can go into a detailed performance level by just changing one of the defines in our compilation scripts. And that gives us a simulation-accurate SystemC representation for all the communication channels. Now, it's still much more abstract than RTL. They saw a 30-fold speed up over the same design running the same data in RTL. But the throughput is accurate. They saw errors that were in the range of 2 to 3% in terms of total cycle count versus an RTL representation. Now, MatchLib is available open source on GitHub. You go to github.com/nvlabs, and you'll see MatchLib, and you can just download it and use it. It's also available with the Catapult. It's shipping with the Catapult high-level synthesis tool. Now, I've done a really brief introduction here. If you want to learn more details, here's a web link that will take you to a talk that was done by Brusek Kalani, who is the lead of the Nvidia project that built MatchLib. And he can talk about why they pulled it together, what it is, and how they used it in the context of their design flow. Now, the key parts of MatchLib are the connections library. And this is a high-level synthesizable message passing framework. it has, and built on top of that is a parameterized AXI4 fabric components that we can use to assemble an AXI fabric. This can also be used to model a number of other buses that use the ready valid data triplets in messages that are passed around, such as tile link, which is used heavily in the RISC-V world. But these parameterized RISC-V components include the AXI components, include the router, the splitter, arbiter, fixtures to go from full AXI to AXI light, and so forth. Now, MatchLib's AXI4 is a class that models the AXI4 protocol using the combinatorial channel on those connections. And you can configure it for the width of the address bus, the width of the data bus, the ID fields, whether we're going to include user fields or not, and a number of other characteristics of the AXI bus, really the full configurability of that resource. And that will define a number of classes and structures that can then be used to send data across the AXI4 bus. So everything is driven off the initial configuration. So this is a struct that you define. It's got a number of enumerated values that give you your data value width, your address width, and sets up a number of configurable options within the AXI4 bus, such as, are we going to use a last bit? Are we going to use write responses? What's our max burst size? Are we using a fixed burst? What are our user fields, and so forth? Once this is defined, it can be passed as a template parameter to a number of the different types that we're going to use to implement classes and structures in modeling an AXI bus. So here we can have an AXI bus, which will be of the type defined in this configuration structure. Once that's defined, if we inherit it into a SystemC component, what we're going to find is that we have a number of different ports declared. So we'll now have a type of R master and W master, and these are read and write masters that will be driven by this module through these ports towards slaves. So here, the data and valid signals are SC outs, and the ready is an SC in. There are corresponding slave interfaces, and here the data and valid would be SC ins, and the ready line would be an SC out. And finally, we have a set of local signal bundles, and these are signal bundles that would be used as local signals for carrying the AXI bus internal to this SystemC module. And all of these types are going to have methods associated with them where we can push and retrieve traffic on the AXI segments as it's being used. So by defining that configuration structure, we also end up defining the payload definitions. So for AW, WB, AR, and R, these payloads are defined, and these are going to be different based on that configuration, but these will have all of the fields that you associate with the 8 different AXI segments. So AW would have an adder, a length, an ID, whereas the write structure would have a strobe, data, last, and we could then take these structures and push them through the master interface. And so here we have a very simple send operation where we construct an AW payload, give it the address, the count, the ID, and we push it into the master the AW segment. And then we can construct the strobe, data, and last and push that into the W segment. And we can do several of those until we reach the count. And then we can pop off of the B segment the response. And we can look at the response. If something went wrong, we can handle that appropriately. So with this capability, let's look at how we would go about modeling an AXI fabric. So this is the example design that we'll be talking about through this little chat. So we have a RISC-V Rocket core, which has two AXI ports on it, one for the local memory and one for I/O. So attached to the memory will be the code space and the data for the program running on the RISC-V. And through the I/O, it will go to another AXI fabric that will be talking to a UART shared memory and an inferencing accelerator. So when we run this system, the RISC-V program will copy features and weights down to the shared memory, and then set some input parameters on the inference accelerator, which will then go through this AXI fabric to pick up the features and the weights, and it will perform a convolution, max pooling, and linear rectifiers as appropriate for the particular layer that it's operating on. And then it will write the results out into the shared memory. So this AXI fabric is going to need to take the transactions coming in off the processor and split them into the three slaves. And this input port coming from the inference accelerator doesn't need to wrap back down to itself, so it only needs to connect to the UART and the shared memory. And so this splitter will have two outputs. And then we need the arbiters that are going to select from the two different masters and send transactions to the shared peripherals. So here I've got a little code snippet, and I will be giving you a pointer to a GitHub location where the full code can be examined, and we've got make files for being able to build it, so you'll be able to look at this in a bit more detail. But here I've got the fabric, and I've included all of the code artifacts that are relevant to the splitters. So we've got a clock and reset coming in, and then we've got our slave ports, and we've got the read port and write port from the CPU and the read and write port from the accelerator. And then coming out of our splitters will be local signals that go from the CPU to the memory arbiter, the CPU to the UART arbiter, and the CPU to the accelerator arbiter, and then the accelerator to the memory and the accelerator to the UART. And so these are local segments internal to this module. And then we will instantiate our AXI splitters, and we'll give it our configuration that describes our AXI bus. We'll give it the number of outputs for the splitters and the number of significant address bits. And so these parameters that go into the template are going to build the correct router for what we're using. This array here for adder bounds allows us to define our memory map for this fabric. So our shared memory goes from 70 million to 80 million. Our UART is at 60 million, and our accelerator is at 60 million, 10,000 hex. Then we can look at the arbiters. So now I've omitted the artifacts appropriate for the splitters and just included what's appropriate for the arbiters. So we have the R master and W master. Again, these are inherited from our AXI configuration type. And these go out to the memory, the UART, and the accelerator. We've got the same local signals that we had in the prior slide where we talked about the splitters. And we instantiate our AXI arbiters, passing in as a configuration, as a template parameter, our configuration, the number of input buses, and the number of outstanding transactions to store in local queues. And after we've instantiated these, we simply hook up the routers. That just got to be too large a set of code to show on one slide. Again, we will be giving you a pointer to a full body of this code that you can look at in a bit more detail. So with what I've described so far, we can put together a complete fabric for the AXI. Now you notice that one of the inputs was coming from the CPU. Now none of the CPUs are going to have models that are available with MatchLib interfaces on them. So we're going to need to bring some kind of wrapper or interface around that CPU model. And we're going to be talking about three different types of CPU models that we'll bring into the mix. One is host code execution, which is going to give us very fast execution and be functionally accurate. We're going to be talking about a fast instruction set simulator, and this is going to run target code, but it's still going to be quite fast and functionally accurate. And finally, we'll talk about RTL, which is going to be much slower, but will give us full clock cycle accuracy. So for host code execution, we're going to be taking the program that would ostensibly be running on the processor and compile it just to run on our host or the simulation computer. We'll then go into the code and make annotations where bus cycles are going to be sent out to the hardware. Now, code side effects or code activity is not going to be included in our simulation here. So our instruction fetches, our stack references, data references, these are all going to be omitted from the simulation. And this may or may not impact your verification goals, but it will be functionally correct. So it may be the best to be able to run it this way and then go back and do slower simulations for performance. If the processor isn't participating in the overall computations, it's just setting some registers and saying go, then this is probably going to be sufficient. So here's what our HCE example would look like. We've got our host program, our AXI fabric, and our peripherals. These are all modeled in SystemC with MatchLib, and we've compiled our host program to a C++ representation. Now, how we pull this in is we create a SystemC module, and we're going to call this host code test bench. And by inheriting our configuration, we get our master ports, which can be driven by our host code program. And we encapsulate this in a thread that gets launched by the constructor. And this thread is, after reset completes, is going to call a function called CPU thread. And that CPU thread can really perform any actions that it wants to. So we're going to do something very simple here as the example. We're going to call this macro tbwrite with 1, 2, 3, 4, and A5. This will write the value A5 to the address 1, 2, 3, 4. That'll get driven on our AXI bus. We'll then read the value back from the same address, and if it's not equal to the value that we wrote, we'll report an error and we'll return. Now, in our final example, we'll be running an entire object recognition algorithm in this thread, but it can be something as simple as this. So now I want to talk about these macros, the tbwrite and tbread. So when we're compiling this program for the host, these tbwrite and tbread will translate into code that references the read master and the write master. And here we're going to do a single read at the address and return the data field from the structure that gets returned by this method. For the write, we're going to do a single write, and we're going to pass in the address and data. Now, this gets embedded into the code, but if we compile this as embedded code, that tbread and tbwrite can turn into address dereferences that will run just fine on a fast ISS or RTL or even a physical prototype. And so by using macros in this fashion, what we're able to do is write a single set of code that can be run on any one of these processor models, and it will create the same bus traffic within the design. Now here we've got single read and single write. We would create macros for 8-bit, 16-bit, 32-bit, and multi-cycle operations as well. This was just simplified down for the slide. So that's how we pull in an HCE or a host code execution program. Now, if we move on to a fast processor model, a fast processor model is going to have code that is cross-compiled for the target processor. It's going to be running actual ARM or RISC-V instructions. The processor simulator is going to interpret those instructions and emulate the behavior of that program running on the target processor. So bus cycles are going to be generated using address dereferences, just like they would on a real processor or a real system. Now, like HCE, the code activity here is typically not included in the simulation. So our local memory is effectively virtualized internal to the fast processor model, which means code fetches, stack, and data references will not be seen in the simulation. Again, this may or may not impact your verification goals. So this is what our fast processor model looks like. We'll have a SystemC process, and it'll have our AXI fabric and our peripherals modeled in SystemC and MatchLib. Those haven't changed from our prior implementation. Rather than a processor model here, we're going to have an AXI transactor. And in the constructor of this transactor, it will launch the ISS process, give it the program to run, and basically configure it to begin executing. And then it will create ports for IPC communication. Now, it's entirely possible that in this AXI transactor, we could be running the full ISS process as a thread. That's a bit more complicated, although it does speed things up a little bit. And so it really depends on your verification goals as to if you want it to be an outside process or a thread. You can really build it either way. So fast processor simulators, there are a number of them out there. QEMU, which is an open source simulator. Spike, which gets generated when you create a RISC-V processor. OVP Sim is a commercial set of fast processor models. AFM is the ARM fast model available under license from ARM. All of these are running from several hundred to several hundred million instructions per second to several billion instructions per second. They are not clock cycle accurate. They do not model caches. They do not have any notion of how long any particular instruction takes to execute. So you have to be a little bit careful with the performance numbers that come off them, but you can count the number of instructions that went by, and that can give you a rough idea of what the performance of a program might look like. Now, each of these different simulators is going to have a different method for capturing bus cycles. We used QEMU, which can be referenced here. And so the methods that I'm going to describe fit that. If you're using a different simulator, you'd have to just go ahead and use a different set of methods. Check with your vendor to see how it works. So on the QEMU side, on the SystemC side, with QEMU, what we would be doing is our AXI transactor, we'd be launching the QEMU process in a thread, in a separate process, with its executable image, kicking it off. It would then create the sockets for the inter-process communication. It would wait on the reset operation for the system, and then it would listen to the IPC sockets, waiting for either a bus cycle or an advance command from the socket. And it would basically run that bus cycle or advance the simulation, and it's going to repeat this cycle forever until the end of simulation. Now, on the ISS side, it gets woken up, given a program. It will then define the I/O region that it wants to trap the bus cycles. So the memory region init I/O is the call that we use in QEMU to be able to define which memory regions we want to be trapped, and then callbacks for read and write operations that happen in those regions. So in those callbacks, we then send the information on the particular bus cycle through the IPC sockets back to the transactor that's in our SystemC simulation. Now, using a TCG plugin, we're able to advance QEMU a certain number of instructions. I usually use about 10,000, but it'll depend on your program and your verification goals as to what exactly you want to use. But so QEMU will advance 10,000 instructions and then communicate with the hardware. Now, if it hits an I/O cycle before it hits that limit, it will immediately run that bus cycle through the IPC channel and against the design. If it doesn't run into an I/O cycle, it will then tell the hardware simulation to just advance. So that's how we're going to tie in an instruction set simulator model. The transactor itself is going to be using those same calls that we described earlier when we talked about the HCE environment. Now let's move on to RTL processor models. So it's important to note that neither host code execution or ISS models are going to be timing accurate. Now the ISS will have some notion of timing, but it's a little bit of an inaccurate number. So they have no model of the code and data accesses that are taking place. They have no model of the impact of caches. AFM can turn on cache modeling, but it slows it down rather significantly. And it has no model of the computation of time as it executes instruction. So if the processor and software are materially involved in the functioning of the system, and the throughput of the processor and software are going to impact your overall analysis of the system, then you need to bring in a realistic model. There's many cases where this isn't the case, and we don't need to go down to an RTL model. But if we do need to, we're going to talk about how we pull that in. Now, just because we have an RTL processor model, it doesn't mean that the entire design needs to be run at the RTL level. We can leave our fabric and our peripherals as MatchLib and SystemC so that we can get much higher performance for the overall simulation, but we'll still have accurate verification of the throughput. So I'm going to assume that most of you pretty well know how to connect up RTL to a SystemC model. This is a fairly well understood mechanism. So I'm not going to go into a lot of detail on the mechanics of hooking up a SystemC function to an RTL function. But there are a few quirky bits when we're bringing MatchLib into the mix, and I'm going to talk about how you would address those. So here is our RTL example. So we've got our AXI fabric, our UART, our shared memory, our inference accelerator. And here we've got a piece of logic that is going to convert from the Verilog to the SystemC. So this is our wrapper. This wrapper actually instantiates all this stuff down here. The CPU, which is in RTL, is interfacing with the code and data memory, which is in RTL. And this AXI segment here is modeled fully at RTL. So we've got RTL going out to this point, and then SystemC from here down through the rest of the system. So our top level Verilog looks like this. This is our top module, and it instantiates our SystemC subsystem wrapper. And it instantiates our Rocket subsystem. Now, both of these get a clock and a reset, of course, but the signals that are passed between them are a set of wires for each of the AXI segments. So we've got an AW ready valid and an AW message, a W ready valid W message. This gets repeated for all of the different segments that make up the AXI bus. And so at this point, these are Verilog wires, and the messages, this message is 76 bits wide, and that contains the entire payload for the AXI structure. Now, the SystemC wrapper is going to be an SC module. It's going to have SC ins for the clock and reset, SC bool for AW ready and valid, and then the message port comes in as a SystemC logic vector of the same size that we modeled in our Verilog. And so those signals are passed back and forth across this array of signals. And so we instantiate our SystemC subsystem, and we make the connections using the SystemC subsystem WCPU, and then the AW segment of that and the message, and we connect that to the message port. Now that's all of the connectivity that we need to plumb in on the SystemC side. From here on, it's just using the same MatchLib that we've been using in all our other implementations of this design. And so once we've got those 76 signals connected to the message segment of the AW port of the right slave out on the subsystem, then everything's done on the SystemC side. Now, on the Rocket core side, we're going to have our Rocket subsystem, which will have a 76-bit vector that's going to be on as a port on this subsystem, and we'll have corresponding message vectors for all of the other segments as well. And we're going to need to convert that AW message into the individual signals that are broken out on the Rocket core RTL. So the Rocket core RTL has an AW length port, an AW adder port, an AW ID port, and so on. And so I use the Verilog concatenate operator to bring these together and load them into the message and pass them on through the hierarchy. You could also index into this. That would be another way to strip out the bits and construct the message. Now, one of the challenges and sort of the quirky bit here that you might need a little bit of help with is the order and size of all of these fields is going to come from that configuration structure that we defined in SystemC at the beginning of this talk. And so what you need to do is go back and dig through the MatchLib AXI code and find the declaration for the various fields. But this turns out to be a real challenge because it's spread across a number of different header files, and it's all dependent on templatized parameters as well as pound defines throughout the code. And that means that it's extremely difficult to just sift through the code and manually figure out what this order is and what the size of all these fields are. So what I do is I compile up the fabric and bring it up either in a waveform viewer, run the SystemC for a dozen clock cycles, bring a traced waveform view up in a waveform viewer, or just bring it up in a debugger and look at the payload structure. And that will show you the order that they've been stored in and the size of all the fields. You can just query that directly with your favorite debugger. And this is much easier than digging through the code. Now, this is a little bit of a brittle interface, but we are going between different compilers, different languages. We do need to be a little bit careful here, and this needs to be this is kind of a rough edge that you as a developer need to take care of. But that's kind of the only bit there that's a challenge in bringing MatchLib into an RTL environment. So now that we've got the ability to pull in these different processor models, we can put a much beefier program to run on those CPUs. So what we're going to do is run a YOLO object recognition algorithm. And this is a fairly lightweight convolutional neural network that will look at an input image and identify a bounding box for a dog, a bicycle, a truck, and a cat. And it's got about 20 different categories that it can identify in pictures. And so we're going to be running this as our stimulus load. And we've built our inference accelerator to be able to perform one layer at a time, doing a convolution, max pooling, and linear rectification of the image under control from our program on the RISC-V. So the RISC-V is going to send down the original image, the weights and biases, and configure up the accelerator to perform a layer, run that layer. Control will go back to the RISC-V when it's done, and it will perform the next layer, setting the hardware in the inferencing accelerator appropriately. So what we're going to find is that the RISC-V will write across this AXI fabric into the shared memory, and then it will write to the inference register bank on the inference accelerator that configures it and synchronizes the activity. It's then going to go grab features and weights, perform the inference layer computation, and write the resulting output layer into the shared memory. And then the RISC-V picks it up and does a little bit of computing and performs the next layer. And that basically repeats. So that's the system that we built and characterized. And so here are the results that we've got. So if we run the processor as host code, so we're going to take that YOLO object recognition algorithm, compile it up to run on the host, completely omit the interconnect. So really, we're just going to make a direct call from this host code to the accelerator, which is modeled as C++. So we really just have a C++ model that implements the object recognition algorithm. We can run an inference in about 12 seconds. Now, as we bring in the interconnect, we can bring in the MatchLib AXI bus and compile it with the defined connections fast sim. So this is going to have it implement the connections, but not the low-level implementation. It will deploy a higher-level implementation that will functionally move the data around, but it won't try to maintain any notion of timing associated with it. So it's going to be more abstract than our timing accurate SIM, and therefore run a bit faster. And here, the runtime for one inference is 1,027 seconds, so about 15, 16 minutes. But quite a bit slower than a pure host code implementation. But as you'll see, this is going to be reasonably fast. So if we take that same host code and we do the connections accurate SIM with the same abstract accelerator, we're going to take about 6,500 seconds. So this is about a 2-hour simulation. Now this degradation here, as we go to the cycle accurate SIM, is probably a little less than you'd typically see in a real design, because we've got a single AXI fabric with 2 masters and 3 slaves. Not a lot going on there. So as we go to the cycle accurate, typically we're going to see a bit more of a slowdown here. Now, as we go to the fast ISS QEMU and keep our connections accurate simulation for the bus, keeping our C++ for the accelerator, it slows down a little bit because our fast processor model is going to run a little bit slower than directly compiled code that runs on our host, but not by all that much. Most of the computation is taking place in the fabric itself, and so we see that slow down to about 7,200, 2 hours and change. Now, if we need to bring in the RTL processor model for accuracy, this is actually going to slow us down a lot from the code execution that we get here. And again, it's going to completely depend on your verification goals and the interaction between hardware and software as to do you need to go down to an RTL processor model or not. For many designs, you'll be able to stop here at fast ISS. But if you do need to go down to the RTL level, keeping the connections accurate SIM, that's the only one that would make sense. So we've got a cycle accurate processor model, a cycle accurate interconnect, and we've got annotated delays on our accelerator. So we're going to have a really good estimate of exactly how fast things will go. This, to run a single inference, takes 97,000 seconds. And for those of you reaching for your calculators, that's about 2.2 days. So it's not really quick, but it runs an entire inference, which is running several billion multiply accumulate operations with literally gigabytes of intermediate data. And so it's reasonably hefty, and we're able to run it in 2 days of simulation at the RTL level. Now, as a comparison point, we went down to the RTL level for the processor, the interconnect, and the accelerator itself. So taking everything down to the RTL level, we actually didn't run the full inference. We ran segments of it and used it to estimate what a full inference would take. And our estimate is that it would be about 2.6 million seconds to do that inference. And again, for you folks going to grab the calculator, that's about 33 days. So really impractical to run even a single inference on this design at the RTL level in logic simulation. Here, we need to really bring in some form of acceleration to the verification in order to meaningfully run this in a reasonable amount of time. So with emulation, we'd be doing this in probably under an hour. But as you can see, with much shorter simulation runs, we can get to a point where we can get very good accuracy. We were within 1% of the RTL accuracy on running this without expending anywhere near 30 days of simulation time. So MatchLib enables us to do much earlier verification at the system level. It allows us to verify what we're going to build with a proven path from an abstract model to RTL, with facilities for verifying that the high-level model and the RTL are equivalent. Into this simulation, there are times when we're going to need to bring a processor in. And the processor can be brought into the simulation in several forms: host code execution, fast instruction set simulator, or RTL. And so this enables very fast functional verification and a slightly slower throughput accurate verifications that are much faster and are able as possible to do much earlier in the design cycle than doing a traditional RTL design. Now, as I mentioned, the full code for these examples that I've described are available at this GitHub location. So I'd like to thank you for your attention and your time here at DVCon today. I've enjoyed speaking to you on this subject. I do have a GitHub location where we've got other interesting source code, github.com/RussKlein. And now I think we've got time to take questions or comments from the audience. Thank you again. All right, are there any questions that came up during the talk? I don't see any in the chat window. Feel free to type something in the chat window, or even unmute yourself and go ahead and shout it out.
This is Jonathan from Qualcomm. This looks neat, but it's still too low level in architecture for where I want to work.
Okay. What level do you want to work at?
I want to be able to take the description of an action and use that to define the operation of my system. This whole address map and contents of the actual implementation of the action, to me, is an implementation detail.
Okay.
How do we move the modeling up to that level of abstraction?
I mean, we as an industry are not there yet. I appreciate the desire to get to that level of abstraction, because I would agree with you. The actual location of peripherals, where they're memory mapped, the underlying details about getting the data to and from that particular peripheral or accelerator, indeed, those are all implementation details. I mean, in academia, there are a few interesting projects where people in the past and currently have been looking at things like that. But we as an industry right now, I mean, most designs are still done at the RTL level, right? we as an industry really haven't moved off of RTL even into doing, using high-level synthesis. High-level synthesis, I think, still is, it certainly hasn't become a mainstream methodology for design, despite bringing in an awful lot of value, right? So you're designing at a more abstract level, you're verifying at a more abstract level. We can show over and over again that your productivity goes up, your ability to look at design alternatives, different architectures is so much greater at that level. Yet, a lot of people are still down at the RTL level. We're going to we as an industry have to start moving up that level of abstraction, being more productive. And we've got to get to this level of abstraction before we can go even higher. At a commercial product level, I just don't think we're there yet.
For me, this is a practical problem. The RTL part is, the digital subsystem for what I'm designing, for what my team is working on, is, that whole RTL part is just a subsystem for, the real part of my design, which is all analog, except for the control.
Okay. Yeah, we don't have high level
for me, this is a practical problem, right? It's like, I don't want to deal, I want to be able to define a reference model for my verification in terms of, not what address got written into that digital block, but what message got passed to define what addresses are going to get written into that digital block. Because the addresses are going to change, right? The number of bits in each register, they're going to change based on some need of some analog designer, right?
Yeah, absolutely. Yeah.
So that's why I'm trying to raise the level of abstraction.
I understand it and I admire it, and I wish I had a better answer for you. But I think we as an industry just aren't quite there yet. But it is an admirable goal, one I fully support. Have you seen, as you're looking for raising this level of abstraction for a mixed digital analog design environment, have you come upon viable candidates in either academia or industry, or approaches that you think look promising?
There is a question Ken has on the chat you might want to address quickly first before I answer that.
Okay, are the quirky bits of hooking up the MatchLib SystemC and the Verilog included in the GitHub code example? Yes, they are. You will find them there. But again, the quirky bit is really centered around understanding that message portion or the payload portion. You need to be able to extract what is the order of the fields within that structure and how large is each one. And you need to do that by going either into a waveform viewer or a debugger of some sort. We don't have an example of performing that operation. So we will show, here's the MatchLib SystemC, here's the order and the size of all the fields, mapping them into the Verilog signal. How we determine those sizes is it's not in code, and therefore it's not going to be in the code examples. So that's something where, as I said, what you want to do is bring that up in a debugger, and then look at that structure in the debugger so you can determine the size and the ordering, because it will change from design to design. This is really a bit challenging. And then Victor asks, are you using TLM to B transport for the communication? No, actually, this is not using TLM at all, because TLM2 does not fully model all of the activity of the communication. And therefore, you're not going to be able to figure out accurately what the throughput will be, right? So TLM2 is not throughput accurate. MatchLib is throughput accurate. And so what you're going to find is actually your MatchLib simulations, they're taking more into account, they're doing more work, so they're going to be a little bit slower than your TLM2, but they are going to be able to give you that throughput accuracy. Now you can turn that off and go faster, right? As I described, there's a constant in there, and you can look back through the slides and find the constants for the detailed versus the abstract simulation. But really, you can think of MatchLib as a replacement for TLM that includes more detail so that you can verify the throughput while you're still at the SystemC level prior to going down to RTL. And that means you can run more use cases, you can look at more performance and things like that. That's kind of the point. Okay, thanks for the questions. So Jonathan, are you finding some viable environments that might work?
I'm doing something right now in UVM with TLM. Okay. TLM 1.0. TLM 2.0 has this generic transaction and stuff like that. I'm using analysis ports because I can do one-to-many communication.
Okay.
And so, and then for this, sequence, this action sequence definition, I'm just using a string hash, an associative array of string as my item.
Okay. So, right. So really, this is homebrew. This is not.
This is homebrewed, but yeah. But it, I can basically say, I have one required field in that hash, which is the name of the action. And everything else is dependent on the action, right? How many parameters it has, how many arguments it needs. Because everything's a string, if I need to send numbers, I just use a string convert, I just use a, some conversion function to cast it to a string. And then when I get it, there's string functions to go either back to real or back to integer, right? So System Verilog has that. Would that work if I were to try to pass this to a SystemC implementation of the same thing? I have absolutely no idea if SystemC would. So I know C
would. I mean, you can really do anything in SystemC. So I mean, because it just diverts to C and it's Turing complete. So I don't know that there are things you can do in System Verilog that you can't do in SystemC and vice versa. It's just which environment are you more productive in and more comfortable with, right?
And is the message TLM compliant? And I guess that's, is it really TLM standard compliant to send a string hash, an associative array of strings through TLM?
Well, yeah, you're not going to be able to.
I don't know, right? I don't know if this works through the through the library of TLM functionality across different things.
Probably. So actually, we're doing the same stuff. Can you hear me? So actually, we're doing the same stuff. So we on the other side on the SystemC, you have TLM B transport. That actually was my question about, and we're sending this B transport over TCP/IP. On the side of the Verilog, we're getting all the data, and we are supplying it to the BFM that actually already generic payload aware. So it's working fine for us. I believe, but I cannot see advantages. Was exactly what I was missing here. So why you're doing this one? So, but on TLM 2.0, you have DMI that actually you can use to speed up the stuff. I'm doing this one all the way, like they sending traffic mostly on the, when they combine the system, they're sending traffic over the DMI connection. So you have a fast transactions.
Yeah, that makes sense.
Yeah, I thought really it was mostly the generic transaction, which to me was not generic enough.
Actually, you have extension for the TLM 2.0 that it can fit whatever you want. ARM actually doing the same stuff. They have an extension on the second part as a part of the generic payload, so you can use it. And actually, I'm using the stuff to transfer the stuff from the SystemC to the RTL.
Okay. Interesting.
Thank you.
Yeah, Jonathan, it'd be great to see a talk on what it is that you're doing.
I think I'm hoping, you know, if I haven't retired by next year, and maybe even if I have, I can come back next year and present something.
That'd be a great talk. I would listen to that one. Looking forward to hearing it. You should send in a proposal on it.
Maybe I can get my boss to send me.
What you're doing sounds really interesting. I find it fascinating.
It's fun stuff.
Yep. All right. I think we're nearing the end of time. If we're done with questions, I guess we're finished today. And again, thank you all for your time. It's been very enjoyable.